Hello, welcome back to Mastering Statistics. Here we're finally going to use Microsoft Excel to solve this exact same problem that we have done, and then later on we'll solve a few additional problems. We have the age of different females getting married in these different states. We have the data that we've collected in each one of these states, and we're trying to do this ANOVA test at a 0.1 level of significance. So we're just trying to see if the population means for each of these states of the age of people that get married, women that get married, if they're the same or not, basically. So what you want to go ahead and do first of all is you go to the Data tab up here. And the Data tab on the right, you notice I have a Data Analysis button. Now you might not have that initially, and this is a Microsoft Excel 2013, I think it is. But anyway, this was not here whenever I started. You have to install it. So if you don't see it there, just go to Google and type in how to install Data Analysis Tool Pack for Microsoft Excel. Basically, you just go into one of these menus, click a few buttons, and then it'll pop up there. It doesn't cost anything. So just go ahead and enable it and you'll see it there. Then you want to go and highlight your data. These are the raw data that you're going to do, and then you hit Data Analysis, and what you want to select is ANOVA Single Factor. We're doing a single factor ANOVA because the only factor involved here is the location of the population. Basically, that's the only control or the only thing that's different there. So you go ahead and hit OK, and a dialog box pops up, and it's asking you for the input range of the data there. Now you need to click that button and highlight and select all of the data, and if you have labels at the top, go ahead and select that too. Click this to force it to accept, and your data is grouped by columns, which means the data for the populations goes down, and you have labels, in my case labels in the first row, and it's asking you for alpha, so you want 0.1. That's your level of significance for your problem. It's going to dump the output, in this case, into a new worksheet, but you have some different options there if you'd like, and then you just literally hit OK, and then it calculates the answer. There you go. Let me go ahead and zoom a little bit. We'll go to View, Zoom, and I'll set the zoom at 145 so you can see it a little bit better. All right, so here you go, ANOVA single factor. This is what all of that work that we did, pages and pages of calculations of all of that data has been reduced down to about 5 seconds, where you can see the fruits of it all. Basically what you have at the very top, this is the actual conclusion down here, and we'll talk about that here in just a second, but up at the top it gives you some additional data. First of all, it tells you that New York, which was the data in the first column, had 10 samples. When you add them all up, it was 201, and when you divide that by 10, it's 20.1. So it's giving you the sample mean. This is the sample mean right here, and then it's also calculating the variance of the data inside of that set of samples, right, which we were doing manually earlier. And then it does the same thing for Texas, how many samples and their average. This is the sample mean. This is the most important thing from there. And Oregon's sample mean. So basically the idea is ANOVA is trying to say, hey, for these different states, these are the different sample means. And obviously it looks like Texas is a little bit different. But statistically, is this enough to say that one of these states' population means of the age of marriage is enough, is actually strong enough? Is it strong enough to say that that we accept or reject that null hypothesis? So here's the difference here. Here's the answer, and this is very similar to the ANOVA table that we created by hand. So you have source of variation. Now the only real difference in Excel is that they use the word groups. They don't use treatments, the word treatments. Most textbooks use the word treatments, but I also told you that they can be called groups. So you have treatments, and then in Excel you call them groups. So you have SST, this is SST, sum of squares between groups, sum of squares among treatments, same thing. This is the number that we calculated before, and you can extend it out a little bit and see a few more decimals if you want. This is the same number over here. And then you have SSE, within groups. In fact, I kind of like these terms a little bit better because they're a little more descriptive. It's a source of variation. It's telling you between the different populations how much variation is there, and within each population how much error is there, how much spread is there. Basically, this guy is SST, this guy is SSE. When you add them together, you get the total variation, which is exactly what we had before. Then it just lists the degrees of freedom. We wrote those down in the table before, and that depends on the problem you have, number of populations, number of samples that you have, and that's the total degrees of freedom. And then this is MST, or the mean square between groups. and this is the mean square within groups. So you got to think of it in terms of variation. You're thinking about what's happening between the different groups. How is the data spread between the different samples that we took, the different populations, and then how is the data spread inside of each sample set that we have. And I've talked about that about 20,000 times up until now, preparing you for this point. This is MST, this is MSE. All right, and then finally, we use that information to calculate F. I'll expand this out a little more so you can see a few more decimals here. This is the test statistic. 2.865079 is exactly what we calculated by hand before. This is the test statistic. All right, so basically this F is the MST divided by the MSE. Basically, that's what you divide these two numbers and you get F. So that's why it's listed in the table like that. All right, so that's that. Now forget about p-value for now. I'll come back to that in a second. The table also tells you the critical value. This is F sub alpha. I was calling it F alpha. Most books call it F alpha. Excel calls it F crit. So basically all you're doing when you get the answer here is you're comparing F to F crit, and you know it's a right tail test. So if this number is bigger than F sub alpha, F crit, then you reject the null hypothesis. And if it's not, then you fail to reject the null hypothesis. Now I went ahead and did this live so that you could see it, but I already calculated this before, and I added a couple of things here that I want to show you. So let me just go ahead and zoom in just a little bit, 145, and I'll push some stuff down. We'll come back to some of the stuff later. I just wanted to show you an F distribution here. This F critical value, this is what Excel is providing right here. F is larger than that. That means you're clearly in the rejection region. So literally all you do after an ANOVA test in Excel is compare this number to this number, and then you either reject it or you fail to reject it. If this number were less than 2.51, over here we would be failing to reject the null hypothesis. Now I have a few notes down here. I've probably said most of them, but I want to make sure that I've said them. I want to point out that all of these values match our manual calculation, so that's good news. SS between groups is the same as the sum of squares among treatments. SS within groups is the error inside of the sample set that we have, SSE. MS between group is the same as MST, and same thing here. I was just basically repeating myself. F crit on this table is the same as F alpha that we've talked about before. It defines your rejection region. If your test statistic falls bigger than F crit, then you reject. If not, then you fail to reject. And so on. This is a review. Null hypothesis is that all population means are equal. Alternate is at least one different from the others. All right. Now the interesting thing here is that, well, I've said over and over again, this test only really tells you if one or more of these guys are different, basically outliers. It doesn't tell you which one. Now you can kind of look at this and see that because it's so obvious. I mean, these guys are equal and this guy was different. You can kind of tell Texas is the outlier. But if you have 15 populations and there are very, very small variations between the two, you're not going to really be able to eyeball it like that. ANOVA doesn't tell you which one is different. It just tells you that one of them, at least one of them, is different, and possibly more than one is different. Well, that's about all I have to say about doing ANOVA as far as how to do it in Excel. Basically, it gives you the raw data, the sample means it calculates along with their variance, and then it just puts the table together in the same way that we wrote it down. And all you can read everything off here: SST, SSE, MSE, MST, the F value, and then the critical value. Oh, I know one more thing I wanted to tell you. Excel gives you one more piece of data, and that's the p-value. And that might confuse some people at first. Basically, you don't really need it when you're doing this, because all you need to do is compare this number to this number. You don't really need the p-value. But if you remember back to hypothesis testing, p-value was just another way to make a decision. It's exactly equivalent to comparing F to F alpha. It's exactly the same thing. Basically, if the p-value that you have for your data is less than alpha, the alpha for your problem, then you reject the null hypothesis. So alpha for our problem was 0.1. That means the shaded area to the right is 0.1. The p-value is less than that, less than 0.1. So that means you reject the null hypothesis. So it's giving you this because it's a computer and it can calculate the exact p-value. Because we do use tables and things like that, it's hard by hand to actually calculate the p-value for these kinds of problems. But basically, it's giving you the information there. So there's two ways to make a decision in Excel here. All you have to do is, number one, compare this and see if it's bigger than F crit. If it is, you reject the null hypothesis. The second way is is the p-value that you calculate for our data, is it less than alpha or not? In this one, it is less than 0.1. Therefore, we reject the null hypothesis. And you can go back to my other lessons a long time ago on what a p-value is, but basically, if the p-value is less than this shaded value, then it means it has to be, that means the f-value has to be over here somewhere, because it has to be a smaller shaded area, and that means it's on the right-hand side of f-crit anyway. If that rings a bell, great. If not, then just, you know, kind of just look at it and see if it's less than alpha, and if it is, reject. So I'm going to go and wrap this up. We're going to do several more of these guys in Excel just to give you a little more practice and some more intuition with using analysis of variance.